welcome to our final talk in this track for the day. I'm now going to butcher that name again. So Antti Kantee,
yes.
I can never pronounce correctly, is going to talk about send and receive of file system protocols. This is work using puffs, and this is the work you were working on last year. It's continuing new work in the same area, I believe, right?
Yeah, something like that.
Okay.
Yeah, it was. Is this on?
Yes.
Okay, good. So it was, as we heard, I'm Antti Kantee, and I'll be talking about the subject on screen. Switch this slide. Oops. So the talk structure, I'm not really talking about paper because the paper was written a while ago, and I keep getting all these new weird ideas, and every time I get a new idea, which is about every 2 days, I'm interested in that, and then I move on. But it kind of follows a general line of thought, and maybe you can rip some sense out of it. So I'll start by just mentioning that I wrote a paper. And then for review, and for the benefit of those who weren't here last year, we'll have an overview of how Userspace file systems work on FBSD. Then just for some non-technical fun, I'll give a history lesson on how I got from the first distributed file system I did to where we are now. Follow little steps. Then we'll discuss some optimizations and speed up for distributed file systems. So especially if you're considering implementing one, you might be able to pick up something. Then I'll shortly present an abstraction for implementing distributed file systems on top of POPs. And the rest of the talk is pretty desperate, so I'll wave hands and give out weird ideas, and hopefully you'll understand and don't think I'm totally crazy. So the paper is first of all quite long, so if you're going to read it, maybe read a couple of pages each night for a month or so. Manage to finish it. Well, actually it's not that long, but it's kind of it's full of little pieces and little niggly bits. So it's kind of divided into two portions. The first portion is if you are actually implementing a file system, it kind of tries to give you an idea about the BSD virtual file system layer, and it tries to explain the different operations in a way which are relevant for distributed file systems and file systems in general, because all of them are there. When you see one fused file systems, it's still not obvious what you're supposed to use it for. But then when you do more and more stuff, you see, so this is where you're supposed to use open and close, and this is the difference between close and inactive and so forth. But that's all in the paper, so I'll not bore you now. If you're interested in discussing the paper, I'm happy to answer questions offline. So, quick introduction. So my current opinion is that a file system is essentially a protocol translator. So it gets a request from somewhere, it decodes the request, and then it transforms it into a form suitable for passing on. For example, a regular local file system, if you want to read a file, it essentially makes it a disk driver protocol request. And then you get the response from the disk driver, and then you interpret it, and then you pass it back. You transform it into a form so you can pass it back. So, that's how I view file systems currently. And my work on POPs allows to implement these protocol translators in Userspace. So this is work which has been ongoing from 2005. And I took a little break and started doing intensive work in late 2006. Pretty much at it ever since. And just something special. Always include a nice anecdote. I don't believe I've ever told this one before, but the initial work on POPs was done on HPPA risk architecture. And when I say it was done on it, I literally mean it was done on it. So the thing is that at the time when I was doing it at home, and I didn't have a proper work chair. But then I noticed, so you know, it's kind of annoying to work if the chair is too low and difficult to type. And I didn't have any suitable phone books or anything, but I noticed that if I took a HP BA132 and put the kitchen chair on top of it, then I could very comfortably work. So, done on the HP BA architecture. Well, okay, the actual first testing was done on Java Station Cross, but that doesn't. I didn't use emulators back then for some reason, and actually, I'll maybe mention later in the talk that I really try to avoid emulators these days also for another reason, because they're difficult. So just to paint the big picture, Fuse is another protocol. So it basically has on a general level uses the same or has the same operations as POPs. Read file, write file, open file, create file, delete file, do this with file, do that with file, crash. If we want to use file systems on NetBSD, so the native protocol is POPs, we translate that to the Fuse protocol by a blob called Refuse, courtesy of Mr. Alistair, nicely seated in the front row. And that's how we use Fuse file systems on NetBSD. And I thought I'd include the Pucker Lansing code this time. So this is just another level of indirection on indirection on indirection. But it brings some benefits, but it doesn't bring all that benefits. So just to have a quick overview of the architecture, we'll talk about it before we go into something else. So actually, if you were here last year, you kind of maybe might recognize this picture, except for one small difference, which I'll get to shortly. So how does this damn thing work? In those cases, it happens to work. So an application wants to do something with a file, create file, read file, write file, blah, blah, blah file. It makes a system call. That's handled by the kernel. The kernel passes it or transforms it into BFS protocol requests. Then the BFS requests are handled by the POPs kernel module, and it transforms those requests into another kind of what I call the POPs protocol, which is then transported to Userspace. And there we have an adaption library, which ultimately calls the actual file server, and which, well, there may be more indirection here, like this can be refuse, so then that's transformed to refuse protocol. This might be a completely distributed file system, so this will call some other guys, call some other guy, and so forth and so forth and so forth, and the abstractions basically never end or the indirections. And if you look at the paper, you'll kind of see the same picture, but it's a slight variation. I just realized I didn't include that picture in these slides for one reason or another. It was here last night. So the one difference to last year is last year this was called Dev POPs, and now it's called Dev Putter. And several people have been asking me, what is this Putter thing, and why do I now suddenly need some extra garbage so that I can use POPs file systems on these. And the point is that Putter is kind of it's the message passing mechanism. So kind of a part of POPs is file system specific, and another part is not. So another part is related to transporting the request from the kernel to Userspace and back. And Putter attempts to abstract some of this stuff. So last fall at some point I did something called PUD, which enables you to implement character and block device drivers in Userspace, which is, well, it's almost exactly the same thing as puffs, except it's a billion times simpler since devices aren't really as complex as file systems. And now both puffs and PUD use Putter thing, Putter whatever, and that's what you need. And ultimately, my kind of vision is to enhance Putter enough so that it will actually be something akin to, for example, what you might find in Mach or some other microkernel system, if I'm allowed to use the word microkernel. Something else important about libpuff, so in addition to providing the interface for implementing file systems, it provides some other lots of auxiliary routines which help to implement file systems. For example, the distributed file systems framework, which I'm going to talk about soon today, if I have time, which I hopefully do since is in libpuffs. And one curious thing is that it implements its own multitasking routine. See, when I started doing this, well, I've never been too fond of threads because threads are kind of difficult to program. So yeah, I thought I'd be kind of clever and implement my own multitasking in the file system library. It works kind of well, but the problem is that, for example, GDB doesn't understand it. None of the standard tools understand it, and well, it works, but it's different. And another idea I had when I started doing this is that, okay, now we push file systems to Userspace, now everything will be fun and games, we'll be laughing all the time, and you know, la 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 la. But it really doesn't work that way. So pushing stuff out of the kernel is just pushing the problems into another place. So if your file system crashes, well, you still can't access your files. You still run into the same problems. File systems are still complex no matter where you implement them. Of course, you kind of get some little benefits, like if your file system or file server does crash, you don't necessarily crash your whole system, which is kind of nice. And actually, as I wrote this bullet, I started thinking, is it easy to add a fail-safe operation to the current architecture? And well, I don't know, since I didn't have many minutes to think about it. But I think it's technically possible. The main problem is that this guy has state and this guy has state, and now if this guy happens to crash, you lose all that state. So you need some mechanism just to sync up with this guy, so you're kind of in sync. So when we get a request from here referencing some object in here, we actually know what that object is and what we're supposed to do with it. And of course, there's other state in here, like some distributed file systems open actual file handles as opposed to NFS, which is completely stateless in that regard. But if you kind of have an open file, if you want to restart, you need to replay that open, so you still have an open handle. So I think it's possible, but it requires some restructuring here. So and some kind of a dedicate or some kind of train of thought or methodology for actually implementing the file servers, so that this fail-safe operation is possible. I don't know, does someone want to work on that? Come talk to me after the talk. So distributed file systems, they're distributed, which is a short way. The funny thing about distributed actually is how I recently began thinking about things. So actually, everything is distributed. Like, well, it's kind of a wild concept, but for example, if you consider a local file system, even if it's in the kernel, it's kind of distributed still in the case that you have the main kernel and then you have the actual file system, and they're kind of disjoint. You can't actually say they're really disjoint, but they're still somehow disjoint. And well, the current ideology is to think local and then move to distributed from that. But I've been sharing some Kool-Aid with one guy, and I think it's kind of better to think of everything as distributed. And then if you want to optimize, you just optimize the local case for the local case. But this buys you the benefits of networked file systems, distributed operating systems, anything, and it gives you it for, well, technically no cost. So the cost just comes from optimizing it for the local implementation. So I think it's a much more flexible way of viewing the world. But okay, let's get back to this talk now. So it's once again really just about protocol translation. You have to translate the POP request into a form which your server or peer understands. So there are two kinds of distributed file systems. There are kind of like traditional client-server file systems, like NFS, so you have a dedicated server, but then there are peer-to-peer distributed file systems, so everyone's a client and everyone's a server, and you never know who's hosting the data, and so forth. Okay, so I promised some mumblings about how I got to where I am today with the state of distributed file systems. So this was done in I think it was November 2006. And one evening I just, I'd heard about. Well, this is essentially the same thing as SSHFS in Linux, so exactly the same idea. So people generally kept saying, yeah, it's good, we should have it, and we should have it. And then one night I just started thinking about implementing it. And the next day I just wrote some, well, again, protocol translation. So I took the POPs interface and transformed it into well, essentially I linked part of SFTP from OpenSSH into the file server. So I just transformed the requests into a form which or function calls to SFTP routines. And okay, it worked. Oh, so that took about a day. Then I actually had to make it work, which took another day. But anyway, and the really, well, I've probably told this a billion times, but the really amazing thing about SSHFS is that if I'd known how damn useful it is, I would have written it ages ago. It just, when I started using it, it was kind of shocking. Like, wow, this is actually good. I can use this for something instead of just, hacking something and then forgetting it and letting it rot and no one uses it and so forth. But the problem with SSHFS, simple SSHFS, is that it was just unit-threaded. It executed one operation at a time. So, for example, if you had two processes, one was, I don't know, creating a file and another was removing a file, they were serialized. So if your server or your latency to the server was great, so you'd have to wait for one response to come back before it would send another. So it's kind of wasn't, for some users it wasn't really efficient, and it didn't do any real caching. We'll soon get into stuff about what we want to cache in distributed file systems, how we want to optimize stuff. So it didn't do any of that, but it worked so well that I don't know if anyone even ever managed to crash it. Of course, it was just a few lines of code. So the less lines of code, the less bugs. Okay, so my next idea was to use the my multitasking thingy, weird hacks in pubs to implement or re-implement SSHFS so that you could actually send or have multiple outstanding operations. So now if one process was removing a file and the other process was creating one, then you could actually send both of them at the same time and independently wait for the response code. So kind of all operations weren't serialized anymore. You could feed them to the pipe as fast as you could, and then you get responses back when you could. And of course, well, one of the problems I'll get into soon with this is if you have very large write or read requests and with very little bandwidth, that happens to saturate your bandwidth totally. So some interactive operations aren't as fast anymore, and so forth. But I'll get into that soon. Like I mentioned, it used the own multitasking system, and for translating the protocol units, it no longer used the SFTP code. So I had to write my own buffer management routine, so I could, add some stuff into the buffer or read some stuff into the buffer without having to worry about mallocs in the application code. So it's kind of, almost like in buffs, but kind of different. And how it actually worked is translate the request, then enqueue it to the server queue, and then the process is put to sleep. And if it gets some or when it gets other incoming requests, the appropriate kind of execution context is automatically woken up, and then you continue from that. You interpret the result and do something else. Blah 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 blah. Okay, then another distributed file system. So I also wrote a 9P client for the Plan 9p resource sharing protocol. And well, there's one fun thing I always like to mention when I talk about 9p is the rename operation. So in 9p it's possible only to rename a file within a directory, so you can't do cross-directory renames, and you can't rename other directories. And this may sound like a bit of a silly limitation, but if you dig into the internals of what you need to do to correctly implement a rename operation, you probably will understand why it's that way. And well, I think one of the best quotes about rename is found in a comment in the Linux kernel in namei.c. So maybe, well, I won't say it aloud, but try to find it from there if you're interested. But anyway, the protocol is somewhat different from SFTP. So, for example, it's more BFS-like in the sense that it deals with objects, so you always operate on an object instead of SFTP, which always operates on a path name. So it kind of has a proper lookup routine and so forth. But really, kind of, a lot of it was exactly the same code as in PH, which I mentioned on the previous slide. It was just, I copy-pasted it, then I kind of modified it very little. So of course, once you copy-paste too much, you automatically start thinking, could we maybe copy-paste less? Because copy-paste is bad, it increases the amount of code, and increased amount of code increases bugs naturally. So I came up with something called frame buff, which is it took the common bits from both of these distributed file system servers and then kind of abstracted them enough and massaged them enough so that they could actually be used by both of them and created a framework out of them. And actually, well, I can notice which shirt I'm wearing, so I started implementing this when at Package Source Con this year, listening to the interesting presentations. Yeah, so what it essentially does, it kind of has this memory management which I was talking about earlier. So where you build your protocol data units and you interpret them, and then it has routines for kind of send, receive, event handling. So for example, when you want to send a request to the server, you just call one routine where you specify the file descriptor you want to send it through, and then kind of the variation of the call. We'll see soon which variations exist. But after that, the framework essentially takes care of sending the request to the server, waiting for the response, reading the response, and then you get woken up when you get a response to your request. So basically, it enables to concentrate on the essential stuff in a file server implementation, how to translate another protocol to another protocol and not worry about how to actually transport the protocol from another place to another, or how to preserve memory for it, or whatever. And even though I'm only my only examples in the paper are client-server file systems, SSHFS, and 9P. I know that the framework is also usable for peer-to-peer file systems, but that work hasn't done by me, and maybe the people who actually done the work will publish it when they feel ready for it. But just so that you know, if you want to implement a peer-to-peer file system, I haven't seen the code, but I've heard a report that it actually works. Yeah, and actually we can generalize the concept. We'll get to that a bit later. Okay, so memory management, well, boring stuff, really boring. You have some object, you write to it, you read from it, you have a cursor to it, you can open a window to it, you can read one byte from it, you can write one byte to it, so forth, so forth, so forth. So basically when you want to implement a file server, you kind of have two layers. You have the layer provided by FrameBuff, which does the actual memory management and so forth, and then you probably have a special layer in your file server which takes care of interpreting it, translates byte or does byte order things, and whatever you need to do, handles stuff like, how do you store strings? Are strings null terminated, or are they Pascal style strings so that you have the length of the string or whatever? And yeah, it's kind of like mbuffs. Well, I don't know. Maybe eventually I'll get rid of my own code and just run the kernel mbuff code, so I won't have to bother with re-implementing thing which already exists. Yeah, and then the send receive part works so that you enqueue a request and then you're put to sleep until you get a response. And how does the framework know which is a response for what you've sent? Well, you have to specify a call where for each incoming transmission from one of your peers, which is might be the server, if it's a client server file system, or just another peer. It's a peer file system. You do a comparison. Is this a response to something, one of my requests, and that's how the framework knows what the actual file system protocol is. Or then you can just enqueue a request to be sent at some point, like you know, if you close a file, for example, why do you really care about the return value of file close? If you can't close it, so I don't know, has close ever actually failed? Well, anyway, but kind of you just enqueue it to be asynchronously sent, but you can specify if the actual protocol expects a response or not, because you need to know for all incoming transmissions, is this a response to something I sent out, or is it something that our peer initiated, and that's the reason. Then there's something which is kind of, if you're familiar with the kernel buff routines, you can send a request and then just attach a handler to it. So you enqueue the request, you don't block yourself, but then later when the response arrives, it's executed asynchronously to whoever sent it. And then finally, incoming non-response requests are handled in a certain way. Well, all this is just technical nibbly bits which I promised to avoid, but I don't know, maybe I didn't have enough slides or something. I got desperate and this promised. So, some interesting stuff. Like I said, SSHFS is pretty damn practical, and I use it daily. And for a long time I used it. I didn't have any problems with it. It worked perfectly. There are measurements in the paper. You can actually see, in some cases, it performs better than NFS in the kernel. That's kind of a small amount of cases, but anyway, the cases exist. And but the problem I didn't notice initially, since I didn't do any low bandwidth and high latency operations. So there were some little problems which I didn't notice initially. And well, I noticed them last year when I spent a couple of months away from home, and I wanted, of course, to play my MP3s from my server at home, obviously. So I had to do a few things to optimize SSH interactive use, optimize read ahead, optimize caching, optimize this, optimize that, so that I wouldn't get choppy playback. I wouldn't if I wanted to switch to the next tune, it wouldn't take too long, and so forth and so forth. Because, for example, one of the problems is if you have a 512 kilobits link and you send like 10 or send read requests for half a meg of data, let's say. You have to wait 10 seconds until any of your other requests are processed, because once you send the read request, the opposite enqueues it, and then it's kind of in the buffers waiting to be sent to you. And for example, SFTP doesn't have any urgent communication. So if you, for example, want to do a read directory or whatever other operation you're browsing the file system, you'll be totally swamped and waiting for stuff. And there's lots of mumbling and babbling in the paper about this, so you can read it from there. Basically, you want to set up things for yourself so that whenever you access something, you try to cache it to a maximal degree at the local end. So, for example, if you've listed a directory and and later return to the directory, then you can get the directory contents without actually consulting the server anymore. So this, of course, has some cache coherency issues, but there are ways to work around these two. One of the interesting things I had to do was something which I ended up calling lazy open. So the problem with open is that SSHFS requires an explicit file handle so that you can read a file or write a file, as opposed to NFS, which has stateless file handles. So you don't really, every time you want to read a file, you don't have to tell the server to open the file. You can just read it. But here, if we had everything kind of cached at the local end already, like the file contents, so they could be directly served from the kernel page cache, but still, due to how things work, we have, or when we get an open request, we still need to open the file handle. And if the channel was busy, like there was a lot of data going on, you would actually block for a long time until you got the open request or open response from the server, and then you could start caching or serving data from your page cache. So that was kind of a very unnecessary wait. So what I did is lazy open essentially opens the file in open, but doesn't wait for the result. And only when you actually do a read or a write, then you check if I've issued an open, and do I have to wait for the response from the server for this open. So that's just the curiosity that had to be. How much time do I have?
7 minutes.
Oh. So I'll better talk quick. So other benefits of this, well, I also did an implementation of PortalFS on top of PUFs, and it turns out PortalFS is really a distributed file system. Details are in the paper if you're interested. Then at some point I noticed that okay, we don't actually have to treat the kernel specially at all. We can treat the kernel where we get our PUF request from as another just a peer to our file system. So I converted that also to use this framework. And for example, if your file server knows that okay, now something has changed at the other end, and now I need to invalidate some stuff which is cached in the kernel, you can just use the routines I mentioned before for doing it. So it gives a request, and then if it cares for the response, it can go to sleep. Otherwise, it can just. Okay, this stuff isn't actually in the paper, but since I've been working on it recently, I thought I'd wave some hands a bit. So last summer I did something which ended up being called RUM. Actually, it was supposed to be called, well, David Holland suggested a name called RUM for runnable Userspace modules, but then someone had committed a driver with the name RUM, so we can use it. So then I, for some reason, tried to add a P to that name and came up with something else. And well, me not being a native English speaker, I just thought it meant food, but it turns out it actually means also something else. Oh well. Well, anyway, it's a shim layer which kind of, because file systems on the top, they're kind of well defined by the BFS layer, but in the bottom they can generally access any kernel routine in a monolithic kernel. So this is just something which mostly through the actual kernel code itself, but it's in some cases, such as the disk driver, it has to implement things in, or it implements things in itself. So, for example, disk drivers just do read and write system calls. But it's a shim layer which allows you to run NetBSD kernel file system calls, well, practically anywhere. I, for example, run them on Linux and so forth. And if you combine kind of this shim layer technology with PUFs, you can actually mount a kernel file system which is actually running in Userspace. So for example, for development, if you want to see, or if you have some access patterns, say, I don't know, some big program like OpenOffice or Firefox happens to crash your file system, you don't actually need to figure out how to run OpenOffice inside the emulator or do complex things like that. You don't need to migrate a real environment into the emulator to be able to debug it sane. You can just run the file system in Userspace, and then when it core dumps, you do something, or then you single step it and so forth. So for the end, here's some weird hand waving. Well, this is kind of what normal kernel looks like. No, I'm not a very good artist, but maybe you can use your imagination. So we have some file systems in there, maybe FFS and TLBFS or something, and they kind of run within the kernel. And this would be the standard microkernel way of looking at things. So we have some scheduling and IPC here, and then we have a well-defined communication channel and isolated file server, and of course I won't get into the whole microkernel performance blah 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 thing, but it's there, and you can't really put this in there even if you want to, even if you know it's good, even like kind of for the benefit of the added performance. So here's kind of what things look like with the rump and puff. So we have maybe some kernel file systems here. If we're developing some other kernel file systems, we can run them outside of the main kernel. Well, for whatever reason you want to run it outside the kernel, it's possible. And once again, here we have some well-defined protocol, but the main difference to the microkernel case is this automatically jumps in here or in here without any code modifications. So it's actually the same code. It's not the same binary though, because there are a few issues, but the same code. You just recompile it. You don't need to modify the code at all. Okay, so then kind of starts getting a bit weird. So this is something I thought of this week or last week, and took a few minutes to implement it. So what I actually now can do is mount an FBSD kernel file system from any platform really, or any system in the network. What I just did was a quick TCP thing. So you mount a file system into the namespace of this kernel or this system, and then the requests go through puffs, and then you have something which says, okay, I'm just a proxy, and then sends it over a socket to another system. It's processed there, and then it comes back. Now, one of the questions which you should be asking is, okay, but how is this different from NFS? And well, kind of, I'd say a good question, but for many reasons. For example, whatever platform you happen to be running this guy on, it doesn't need to understand nothing about NFS, because this protocol is completely contained in well, actually it's contained here. This picture is drawn wrong. Blame someone for it. And it doesn't. The kernel on this system doesn't actually have to know anything about this, how to transport requests to this kernel file system. So it's just a self-contained user space binary. And well, here's kind of the thing I would really like to take things to. So kind of instead of having the kernel at the center of the universe, we kind of, it's not anything special. You can push it somewhere, just treat it as anything else, and we kind of have a great big file server here, and our peers are there, and kernel is there, and it does service advertisement and web services and so on. conclusions, which I think I have about 2.5 seconds for. It's possible to implement distributed file systems. It's easy. The speed argument doesn't really count always. Sometimes it counts, but not always. Usually not. Usually other things way more. Abstraction is nice. That helps implementing feature bits. You can kind of take a scientific approach to optimizing performance, or you can kind of take a hack after hack approach, which tries basically that. But of course, the hack after hack approach, as we all know, has the problem that once you add another hack, something else breaks. And on a fundamental level, everything is distributed. So if you want to do something, we have a few summer of code projects, some other stuff. Come and talk to me, ask questions. Thank you very much.
Want to go for a couple questions, or?
Questions? Audience. Anything to show you? Well, currently it's running Windows, so I can show you crashes. Well, I can show people later, but it's how interesting is to type command. Okay, I can show you.
Well, let's thank the speaker. This is the last session for today. Dinner is at 6 o'clock in the same place that we had lunch, so you're free until then. But that's on the second floor. So, thank you.